using the blackboards?
Yeah.
Okay. Here you go. Oh, left on and raise the screen.
Oh, wait.
This right here.
Oh, yeah, thanks.
Using the blackboard?
Yeah. Oh, okay. So, my name is Swastik Kopparty. I work in theoretical computer science. And so, the topic that I will talk about is supposed to be topics in randomness and error correcting codes. So, I thought I would first start by giving a sort of state of affairs of what are the burning questions in computer science that are related to what I work on. And then based on that, I'll then motivate my two favorite problems, and which are the problems that I plan to work on while I'm here. Okay, good. So the very broad area is randomness in computation. And it has to do with the very perplexing state of affairs that we can do a lot more with probabilistic algorithms than what we can do with deterministic algorithms. And addressing this issue is the topic of this subject. So, I'll start off by giving a concrete problem and a really cool randomized algorithm from long ago, and it's a really short algorithm. It's a really neat example to know, and then I'll start with that. Okay, so the problem is that of finding square roots mod p. Okay, so I give you a prime p, I give you a number a which is between 0 and p minus 1, and I ask you find the integer b such that b square is congruent to a mod p. Okay, so okay, and the goal is to try to do this efficiently. Try to do this as quickly as you can. So find b such that. Okay, so how would you do it? Oh, right, good. Yeah, exactly. So okay, so okay, good. So so first a simple observation. Let's say p is 3 mod 4. Then there's actually a simple formula for the square root. Then so if p is, then b you can take to be a to the p plus 1 over 4 or something like this. Okay, but in general this is a pretty serious problem. And okay, so one of the first randomized algorithms ever discovered, I mean, I guess after Buffon's needle, is the following. So it was from Berlekamp in 1962, and it's and so the algorithm is really cool, and the philosophical question it leaves after that is even worse. So okay, so here is the algorithm. And the okay, so notice that finding b like this is exactly the same as the problem.
Log p to a power, right? Which is squaring. That's what you're aiming for.
Oh right, exactly. So I mean the goal is do this in time polylog of p. So this is the kind of time that I want to solve it in, because I mean, so this is a reasonable thing because it takes polylog p number of bits to represent the number p. Okay, so the problem of finding the square root is exactly the problem of factoring x square minus a mod p, or yeah, factor x square minus a. Okay, so the step number 1 is, okay, I'll pick alpha and beta in fp uniformly at random. Okay, so I've already started using randomness. Okay, consider now the new polynomial q of x, which is alpha x plus beta square minus a. Okay, so I did a random affine map on the field fp. So previously the roots of x square minus a were b and minus b, the thing that I wanted to find. After having done this, the roots of q of x are two uniformly random elements of fp. Okay, so is that clear? So I took a random affine map on fp. This permuted the elements completely. So now the roots of this polynomial are two uniformly random elements of fp. Okay, great. So at this point we're almost done. So the last step of the algorithm is take GCD of the following polynomial, x to the p minus 1 over 2 minus 1 with q of x. Okay, so what does this do? So the polynomial x to the p minus 1 over 2 minus 1 is the polynomial whose roots are the quadratic residues. So the only property that I am using about it is that it is a set of half the size of fp, and it is a polynomial which is sparse. So doing computation with it can be done efficiently. So q of x is a polynomial whose roots are two independent numbers in fp. I took the GCD with a polynomial whose roots is exactly half of fp. And so when I do this with probability half, I am going to split the roots. I mean, the one root of q of x will be a root of this polynomial, one root of q of x will not be a root of this polynomial. And so upon taking the GCD, I will find some x minus gamma, which is a factor of q of x.
You don't really need alpha, it's enough to take beta, right?
Oh, right, good. But then you need to know how, that quadratic residues differ by beta and something. So okay, so I didn't need to take alpha, right? Great. So okay, so that's a pretty cool algorithm, you must admit. Okay, good. So and in fact, the property of this algorithm is that, look, when it produces a square root for you, it's never wrong, right? I mean, once you get the square root, you can verify that it is indeed the square root. So what exactly did the randomness do for you? Okay, so I mean, for all practical purposes, I can always pick a random alpha and beta, by closing my eyes and doing something so that it has nothing to do with my problem. But right, so what is randomness doing? Okay, so the big question, and so this is one of my favorite problems, is so do this deterministically.
A is fixed.
Yeah.
Stuff gives it feedback.
Exactly, right. So there is a known algorithm that runs in time polynomial in log p and a, not log a. So for instance, it's easy to find the square root of 7 mod any big prime, but 7 had to be a fixed 7. So the running time is something like 7 times log p. Okay, so this is the question. Do this deterministically. So what is known is so for when a is a constant, you know how to do this. It's also known that under the generalized Riemann hypothesis, this can be done. So very.
I think that sort of makes clear what one should do.
Oh, right. And that is the problem that I want to work on. Right. Good. So yeah, good. Okay, and so another problem that this.
By do this, you mean a deterministic way of choosing A and B so that you know it works?
So that would be one way, but but ultimately just find square roots mod p deterministically. And so the status is that there is a randomized algorithm for doing it. There should be a deterministic one too. Does randomness really help? Are randomized algorithms really more powerful than deterministic algorithms? If you think the answer is no, then you should be able to do this deterministically. So it turns out that this problem is also equivalent to the problem of find a quadratic non-residue mod p. Yeah. So I give you p, find a quadratic residue mod.
With what constraints?
Anything whatsoever.
Quickly.
Yeah, quickly. In time log p to the order 1, find 1. So there is a famous conjecture of Vinogradov that says that there should be such a quadratic non-residue in the first polylog log square, I guess. with the first log square numbers should be a quadratic non-residue. This is implied by the generalized Riemann hypothesis, and but here I'm giving you much more liberty. You can do anything you want. Polynomial time algorithm. It doesn't have to be in some nice interval. It doesn't have to be.
What's the relation between these two things? So you say that's equivalent to the.
It's equivalent to the problem of deterministically finding square roots mod p. Oh, okay. So
You should point out square roots is not finding discrete log. It's much easier.
Oh, right, certainly. So I just gave a randomized algorithm here for it. So people right. So discrete log, we don't even know a randomized algorithm for solving in time polylog p. But here I give you a randomized algorithm, and for many primes, I mean already half the primes I just gave you a one-line formula. So so do this in general. So this is the first problem, and I hope you agree it's perplexing. Okay, good. Okay, good. So I'll now come and I'll tell you about my second favorite problem. So okay, good. So this has to do with probabilistic construction. So it's again the topic of randomness in computation. Okay, so here unlike the previous problem where I was trying to solve, I mean I had an algorithmic problem. There was some input and then I want to come up with the unique answer that has some property. Here I just want to find a set which has a certain property, and okay, so the specific problem that I'll talk about here is the problem of constructing error correcting codes. Okay, so very quick definition. So if delta is a number between 0 and 1, then so delta error correcting code is a subset C sitting inside 0 1 to the n, such that every two elements of C which are distinct are actually far apart. They differ in many coordinates. Okay, so so for all x, y, and not equal to y and C, x and y in at least delta n coordinates. Okay, and the setting is delta is a constant and n is going to infinity, and okay, and so so this is like a well spaced set sitting inside 0 1 to the n. The objective is to find the largest set C, or find a large set C that that has this delta error correcting code property. Okay, and so there is a trivial argument that shows that if you take maybe I'll do it. How large do I want C to be? Well, as large as possible is the question, and so now I'll make an observation that there is this very simple if you take C to be a random set, then it will have some size, and the question is to find such a C deterministically. So right, so observation, pick C in 0 1 to the n uniformly, so either uniformly with a little bit of fudge, or as a random linear space over F2, that is. Of size 2 to the n divided by the volume of the ball of radius delta n. Okay, so if you look inside 0 1 to the n, look at the set of all points that are within distance delta n of a fixed point that has some number of points. Look at 2 to the n divided by the ball of the volume of that ball. This is a natural number related to, well, it's not a natural number, sorry. It's It's a
Canonical.
a canonical number, right? It's a canonical number related to that problem, good. So if you pick a uniformly random subset or a uniformly random linear space of this size, then it will have that delta error correction code property with high probability. And the question is to find just even one not one, so n is going to infinity. So for every n, just find one example of such a set. Okay, and so unlike the square roots problem where there's an input and you may have to process that input and do all kinds of things with it, here there's no input at all. It's just one for every single n, and the space of possibilities is extraordinary. And so the question is find such a thing, and such a thing is not even close to being known. So good. So just to make that precise, so this thing is roughly of the form 2 to the f of delta times n, and we cannot find and at least the best known constructions of set C with such a property have 2 to the some different number as a function of delta times n. Okay, so what do you get from expanded graph? So, well, some different function of delta times n, and it's differ. Okay, great. So
What does it mean to give
What do you mean by explicit?
what do I mean by explicit? So if so for the n, you should come up with an algorithm that runs in time polynomial in n, and you should give me, say, a basis for the linear space that has this property. So that could be explicit. Okay.
How do Hamming codes or sort of perfect sphere packings over F2 fit into this?
Oh, so good. So you may have heard of Hamming codes and a different regime of this error correction problem. So Hamming codes, for instance, fit into the regime where delta n equals 3. Okay, so right. So here I'm looking at the regime where two different code words differ in a constant fraction of the coordinates, and not just a constant number of coordinates. Okay, great. So okay, so yeah, just to wrap up, so so both these problems have been very well studied, and there are a lot of things that come up in attacking problems of this kind. So this is somewhat a new territory for me, but I work a lot on error correcting codes, and the topics that come up are related to many things like algebraic curves, rational points on them, polynomials, finite fields, all kinds of combinatorics. So yeah, so in particular, it's very likely one of you has the tool that will have the solution to one of these problems or something. So I look forward to talking to a lot of you and finding out things.